Welcome back to the Student Hub Live STEM Showcase. Well, in this session, we are hearing about mathematics and statistics. And I am joined by Mark Pardas and Robert Bignell in the studio today. Now, Robert, you're going to be talking about the four-colour theorem.
Yeah.
And Mark, you're going to be talking about chaos theory and the butterfly effect. Not things that I was expecting to hear about in the mathematics and statistics session. But we're going to give students an example about why maths and stats is such an exciting area and really how it can be applied and how it is taught.
Yeah, I think that's exactly right, yeah. So, I mean, my particular area, the four-colour theorem, actually is a really stupid example because actually its applications are pretty limited. I mean, you'll find out in a minute, it's not actually very useful in real life, but the area of graph theory, which underpins it, is really important. So.
Now, you got into graph theory, which I'd actually never sort of thought, oh, somebody would be really into that sort of thing, but it's an interesting way that you got into it.
Yeah, I mean, so, well, when I started as an undergraduate and I was, doing maths, and, maths is all about equations and integrals and things like that, and you get to sort of third year and it's beginning to get a bit complicated and you sort of piled layer upon layer of stuff. And then I went on this lecture course called Combinatorics, and it just started from first principles, and suddenly instead of writing loads of equations, you were just joining dots with edges and arguing about little pictures, and that simplicity in a way, rather than the technicality of the maths that I've been doing up to that point, really appealed to me.
Because so many students say that they're off-put from things that involve maths because they don't like, or they had a bad experience at school with maths.
Yeah. So I mean, for me, maths is a very visual thing. It's a very intuitive thing. And somewhere in my undergraduate, I sort of lost that and I regained it when I went to postgraduate stuff. And I think intuition is a really important part of learning to do maths.
And this four-colour theorem is a really good example because, I mean, it was a genuine, whilst you say it's not very interesting or relevant, it was a genuine problem that, I guess it has an interesting approach and way of demonstrating things.
Yeah, exactly. So, I mean, it started like 150 years ago, about 1850, and there was some 20-year-old guy was trying to colour in the counties of England. So I brought an uncoloured counties of England here, and they were trying to colour it in, and he noticed that you only ever needed 4 colours to do it, so that no two counties which shared a border had the same colour. So
now, why was he doing that?
Goodness only knows. I mean, he did become a mathematician actually in his own right in South Africa years later. But at that point, I think he was studying law. And he, anyway, so began a legend, if you like, where he went, you can do it with just 4 colours. And it's always true, you can always do it with just 4 colours. So to demonstrate that, here's one I coloured in earlier. And so we have, an example where all the counties, these probably weren't the counties that were around in 1850, but here are all the counties, and you'll see whenever there are 2 counties neighbouring, they have different colours, and that's kind of the important thing. But this is literally the only application that I know of the 4-colour theorem that says for any map, you only ever need 4 colours. But in real life, I mean, cartographers will use 5 or 6 anyway, because you can get a much more aesthetically pleasing looking picture.
But the idea, I guess, is about finding a problem and, I guess, agreeing the smallest amount of steps necessary to be able to solve that problem.
Yeah, that's right. And, that's the sort of general approach in maths and in other parts of maths, and particularly in other areas of graph theory, which is the stuff that underpins all the proof that went into this. It really is, sort of quite... That's kind of important because you need to optimize these things. Nowadays, we're dealing with enormous networks. Think of Facebook or something like that. You've got millions of users, and you need something that's going to be really efficient. And so the difference between 5 and 6 colours or 4 colours could actually be really important. I mean, for whatever problem you're looking at.
Okay, so how does this then relate to graphs?
Yeah, okay, so I've got some slides which maybe we can show up.
Yeah, we'll show them on the screen.
So if we start with our map of the counties of...
here we are.
Here we are, yeah, so we got the map of the counties. Now, the first thing you do is, instead of counties, so I want to turn this into a mathematical problem. So if you draw a little dot on each of the counties, like that's brilliant. So we're going to call these little dots, they're going to be called vertices. That's just the technical term we have. You might like to call them nodes or something. They don't represent cities, I just drew the dots on randomly. And then what you do is you draw a line between any 2 dots that share a border, like that. And then if we go to the next slide, you'll see I've just sort of grayed out the map. So what we're left with now is a mathematical object where each of the dots represents a county, and the things that connect them represent whether they share a neighbour or not. So, and you can see at the bottom the Isle of Wight is there sitting on its own because obviously there's a band of water between them, so that it's not connected to the rest of the network, if you like. So that thing is a graph. And so the four-color theorem in this setting says that you can color in the dots or the vertices of this in such a way that using just four colors, no two dots which have a line connecting them have the same color.
Okay.
Yeah, so now if we go on to the next slide, so now I've highlighted the East Midlands. So here's an example of, so the four-color theorem says you need at most four colors, but here I'm going to show you that I definitely need all four colors in this particular example. So here I've colored in the East Midlands red, and you'll see to the north is Staffordshire, which is green, and then down in the sort of, where's that? Southwest, my direction's only a compass.
The problem's when you make a graph and not a map.
Exactly. So you'll see that so far we've got these four sections, these four counties, and you'll see that you really genuinely need four colours for this, because in the middle you've got well, it's Birmingham really with the red dot, and it's adjacent to all three of those other ones, and then each of those other ones are adjacent to all three of the others. So if you had any two of those with the same colour, then they'd be next to each other. So you definitely need four colours for this. So that's kind of the arguments that we use in graph theory. Now
you said this started in the 1850s.
Yeah, that's right.
And why is it still relevant today then?
Well, okay, so I mean it's in an area of graph theory, and you know, sure, the applications of this particular thing are a bit silly, but obviously you've seen these pictures of networks. What does that remind you of? Computer networks, this, that, and the next thing. So there's a lot of, there's a lot of stuff now. Data science. We have a new data science qualification in maths, in maths and stats and computer science, starting in 2019. And this is a big area at the moment, and there's a lot of stuff going on because you have social networks, you have big data, data mining. Of course, we've seen all the Cambridge Analytica stuff recently. Sorry to say, they're probably using graph theory techniques and doing some of their data mining.
And because you've been talking in another video I saw about 6 degrees of separation, and you're mentioning some of the application with Facebook and things.
Yeah,
and
right.
How does this then relate to that?
Yeah, okay, well, so I mean, basically there's sort of two sides of the same sort of pure mathematics research area, if you like. So we have, on the one side, we're trying to colour in the vertices, and maybe that is useful in some ways, maybe it's not, who knows. There are certainly algorithms where they want to do this sort of thing. They tend to be slightly nuanced and not so directly obviously applicable, but it's all studying these graph structures, so that's kind of where it comes from.
And tell us then, like you mentioned this four-colour theorem, and this was something that's been proved, and that's quite an important point, isn't it? Because after 120 years later, we're now able to say actually categorically this is a truth, which is not something that one can say in many STEM subjects.
Oh, right, exactly. I mean that's the thing about maths, in particular pure maths. Sorry, Mark. But, particularly in pure maths, we can come up with things. We can have the intuition that tells us this is definitely true, and we can come up with sort of bogus arguments that explain why it's always going to be true. But unless you genuinely have a mathematical proof, you can't claim that as a result.
So how did you get the mathematical proof then?
Okay, well, so the mathematical proof was, as I say, it took a very long time to come. It was in the 1970s when it was finally proved, and it was done by two mathematicians come computer scientists. It's kind of somewhere in between.
But we're claiming them as mathematicians.
In Illinois, and they got a supercomputer and they sort of threw a supercomputer at it. There were hundreds of thousands of cases to deal with, and they came up with thousands of pages of computer printout, and this was apparently claimed to be a mathematical proof. Now, a lot of people were very sort of skeptical about this. It was the first time a computer had been used to prove anything. And it isn't a very beautiful proof because, it's huge volume. And it took years before anybody was actually really able to verify that this was indeed actually a proof. Right? Yeah. So it's a bit of a unique one. Well, it's certainly the first time a computer was properly used to prove something.
And you said earlier that this is, this whole idea sort of really excited you at the time. You're now researching in this area. What are you doing? Yeah,
so I do something similar, and it's... I work sometimes in graph theory, sometimes in other little combinatorial things, but it's always about studying structures like this, and usually I deal with something called infinite antichains. I'm just going to throw that out.
Sounds good.
Yeah, it sounds good. And it basically means, so I showed you what a graph looks like, and imagine an infinite collection of these graphs, all of which somehow can't be compared to one another. So that's the kind of stuff I deal with. It produces lots of pretty pictures. And it does also have serious applications in sort of computer science, algorithms and so on.
Now, we know students love colouring in,
Yeah.
but aside from that, how might this link to curriculum?
Okay, so, well, actually, I mean, this, we have in our third year in Maths and Stats, we have a course called MT365, Graphs, Networks and Design. So, well, I've just told you what a graph is. A network's essentially the same thing. Design is something different. And in that, and I didn't realise this until recently, there's a DVD pack, which is like this. It's not a very exciting cover, I'm afraid. But in here, there's a whole series of videos, but one of them is about 4 colours and the 4-colour theorem, which is put together by Robin Wilson, who used to be an academic here. And it's a BBC OU co-production. It's about 25 minutes long, and it gives you a real in-depth sort of history and the mathematics behind it. So if you studied MT365 and you haven't looked at it, really do look at it, because it's really brilliant. And if you haven't studied MT365, then sign up now.
Yes, we've been talking about choosing various qualifications and pathways. From your perspective then, what sorts of attributes or things do you think students need to have to really enjoy going into this particular area?
I think you need a certain amount of you need some kind of ability to visualize these things. You need to be the kind of sort of mathematics. I mean, you do need some mathematical background, not a huge amount, as to be said. This has considerably fewer requisites than a lot of our third-year courses. But you need a certain amount of sort of intuitive visual thought. And, of course, you need to be rigorous, because in maths, you always have to be rigorous. So, yeah, you need to check your details very carefully.
Brilliant. Right, that's excellent. I'd just like to take a quick trip to the hot desk and see how everyone is at home. Scott and Sarah, what did the audience make of that?
Everyone's getting really involved on the website at the moment. All of people are talking about the different ways they've come across these things in the maths area as well, and sort of the TED Talks and things they've been watching, and just the fact that maths can be such a visual explanation of things as well, because you usually see it as just sort of numbers.
That's right.
And that's really great. And obviously make sure to grab your 4 colours and get involved as well.
Excellent, Scott. I see you're doing some yourself. Keep on the hot desk and keep chatting to everyone at home. That's excellent. Well, thank you so much for that. I'd like to talk now about the chaos theory, because some of our crew here are in a band called Chaos. I'm very interested to see how you've developed a theory about that.
Well, first of
That's a joke. Don't worry.
I haven't developed the theory about this yet. But I'm sure that we are all now familiar with the word chaos. It's in the common usage. And when we say chaos, typically we think about something that is disordered, confusing, and these type of things. So in mathematics, when we talk about chaos, we typically think about a type of movement, so a type of motion. So when you look at chaotic system, usually it's like very disordered looking, moving in time. And also it might appear to be random, so it's changingly at positions and over time at different, in a way that seems stochastic and random. But I should say that it's not random, it's always deterministic. That's the property of a chaotic system. But there is an important feature of a chaotic system, and this is what is called that a system is very highly sensitive to the initial conditions. So, and perhaps to define this, I should first explain a little bit, put a bit of background here.
Yeah.
So chaos theory is studied in the branch of mathematics called dynamical systems, which is a very important branch in both pure and applied mathematics. But in applied mathematics in particular, we typically deal with something called differential equations, which means that we study the motion of some things. And typically, if you have a differential equation, which is just a mathematical equation, and you know the initial state of something, you can predict the future of this state. So that's what these dynamical systems gives you about. So now, when we talk about chaotic systems, and first I should say that these dynamical systems means that they are deterministic, so that you can predict the future given the initial state. But when we have a chaotic system, we have a very sensitive dependence on the initial conditions. So this means that if you slightly change your initial condition, this may lead to a very completely different future state. So that's the concept of being very sensitive to the initial conditions. And this is what is linked to this concept of the butterfly effect, which nowadays has become very popular thanks to Hollywood films and science books.
I was going to ask, why is that word used?
Well, that's maybe I could put some history here.
Yeah.
So the chaos theory was actually discovered in the late 19th century by a very famous mathematician, Henry Poincaré, who was studying the problem known as the three-body problem. And this is the problem that has celestial bodies acting under the influence of gravity, for example, a star and 2 planets. So back then he was looking at the solution of this problem, and he observed that some of these solutions were exhibiting this type of erratic and kind of disordered-looking behavior, and they were very sensitive to the initial conditions. So he was the one, in a way, to discover this chaotic motion. Although back then there was no computers, there was nothing that could be proved visually to see that this is actually what happens. And although there was some mathematicians that worked on this during the first half of the 20th century, notably the Mary Cartwright and John Littlewood from Cambridge that did also some work on this, it was not until the 60s when computers came to play a big role in science research, when there was this famous American meteorologist called Ed Lorenz, who was studying a mathematical model to describe the atmosphere of the air on the planet Earth, in a way to try to understand how to predict and how to forecast the weather. So what he discovered is that it was actually by chance. So he was solving this equation in the computer, and then he was starting from an initial condition, then solving the equation, and then predicting the future state of the weather. But then he thought, well, I'm going to try and save some time, and instead of starting from the same initial condition, I'm going to start from halfway through of this computation. So he did this, and then to do this, he printed out some of the numerical values of the original computation, and then took this numerical value to put as the initial condition of the new computation. But the problem was that this numerical value that was on the printout was a rounded value, up to 3 digits, and the computer was working up to 6 digits. So there's a difference on the initial conditions. And then he discovered, by chance, that when he put this rounded value, the trajectory was completely different to the previous one. And then looking back at what happened, then he realized that was because of this rounded value in the printout that he was using. So that was the first discovery using computers of chaos. And then that was in the 60s, and then in the 1972 he went into this conference paper that was very famous under the title, "Thus the flap of the butterfly wing in Brazil set a tornado in Texas." So meaning that a tiny perturbation somewhere can actually change the course of a tornado somewhere else. So that's the idea of this butterfly effect. And then the butterfly effect was made famous in a book written in the 80s by James Blake, where basically he introduced this concept of butterfly effect based on Ed Lorenz's work in the 70s. And nowadays this has become very common, this concept of making small changes and having a large effect in the future.
Wow.
So that's the history behind it.
Okay, brilliant. Now, you've prepared some videos
to
see how it works.
Yeah.
Not with real butterflies.
No, not with real butterflies.
What are we going to see in these videos?
So we're going to see, well, first I should say that we're going to see a numerical computation of some mathematical equations that model some mechanical systems.
Okay.
And one of them is non-chaotic, and the other one is chaotic. So we'll see the difference.
Okay.
So in the first video, we'll see a single pendulum, which is a ball attached to a string, and then it's oscillating around a fixed point. And then the first video, we're actually looking at 2 single pendulums. They are independent, one on top of each other.
So we can see one here. This is the 2 single pendulums. And
they
you
are
can talk
identical.
Over this.
We have put 2 different colors, red and blue. And we see that here we started from initial positions which are exactly the same except for 0.1 degrees. And as expected, this is well, we know that a single pendulum has a simple periodic motion, goes left to right, and we understand this very well. So as expected, we don't see anything surprising here.
No.
So now in the next video, we're going to put some complexity here, and we're going to study the double pendulum, which we put another pendulum attached to the first ball, and then we have 2 balls that can oscillate. So this is one of them.
Okay, so let's take a look at that.
And then we see that now the dynamics is slightly, well, it's a bit more complicated. So we see that the second ball starts to make some funny movements. It goes to the left or to the right. So it's rotating. So it appears that it's kind of always going to the left or to the right in a rather random way. So you can't really, it doesn't seem that you could predict this future. But the important point is that chaos, if you know the exact initial solution, you can predict where it goes. But now we're going to illustrate the essence of chaos and this effect of being sensitive on the initial conditions. So in the next video, we're going to plot 10 double pendulums. They are independent from each other. And then they are plotted on top of each other with different colors. and they start from the same initial condition except a tiny fraction of an angle. So it's 0.1 degrees apart from each other. So this is very tiny, so you cannot, when you plot them on top of each other, you cannot really see them, and you can only see one of them. And let's see what happens when you plot them all together. So here we can only see one double pendulum, but then at some point we'll see how all the 10 pendulums unfold.
So is it random or not random?
No,
if
it's
you
not
can
random.
predict it, is it chaotic?
Sorry?
Is it random or not random?
No,
I
it's
mean, if
not
you can
random.
predict it, it's not randomness.
No, it's not random.
Because you can predict something if you know the exact extent to which things are different.
That's the profound message of chaos, because up to the 60s, everyone thought that a deterministic system could be predicted.
Yeah.
But now what chaos is telling us is that if there is some uncertainty on your initial condition, which is always happening, because when you do some measures to predict things, you always have some error experimental, for example. Even though this tiny initial uncertainty can lead to completely unpredictable results. So we can see that, we could see in this video that there was, during the first 10 seconds, all the pendulums follow the same trajectory. And then after the 10 seconds, all of them started to follow different trajectories. So we can see that we can predict up to some point, and then after that, things become completely unpredictable. And that's the essence of chaos, which, as Lorenz realized, it has an enormous impact on weather forecast, for example. Because now something that he was expecting to be able to predict, he realized that actually is unpredictable, because you will always have some sort of uncertainty on your initial conditions.
Right, a shame for weather forecasters. But what you're both talking about ultimately is the importance of modelling, of being able to use mathematics to predict the future, which is an incredibly powerful thing. And I know when I did a lot of statistics, I was just amazed at the extent by which you could, understand the importance of certain variables in predicting something for the future. And I found it such an exciting way of looking at the world. Instead of being very retrospective, it's about using the past to really make predictions about the future. And you're both doing that, but in really, really different ways.
Yeah, different ways,
Yeah.
In applied mathematics, usually we try to apply mathematical methods and mathematical equations that try to model real applications in physics, chemistry, biology, economy.
Yeah, I guess in pure maths, our view is the other way around. We play around with things and we have a lot of fun and we come up hopefully with nice theory, and then at some point we have to tell funders and so on why it's important. So that's the way of being a pure mathematician. But when applications come along, it's really it's really rewarding as well. And there's plenty of cases of that in pure maths over the last 100 years or so.
Brilliant. So I want to talk then about how all of this matters. And firstly, in terms of the chaos theory, how does that link to curriculum and your own research?
Well, in my own research, I work on different projects. One of them is chaos theory. And for example, one of the key questions in chaos theory that has been, or most of the researchers have been working on, is trying to control chaos and whether you could extend this predictability time in a chaotic system. So something that we did last year in a very recent work in collaboration with Michael Wilkinson from our school as well, we saw that in some systems you can actually extend this predictability time by adding some sort of external fluctuations. But here I would go into perhaps too much technical details, but the idea is try to understand whether you could extend the predictability time of your chaotic system, which eventually this would have impact out of applications, for example, in weather forecast, if you could predict for longer than expected, for example. So that's from a research point of view. And in our curriculum, chaos theory is covered in one of the modules, which actually is this one here. It's MS3 to 7. It's a level 3 module.
No butterflies needed?
No butterflies. Actually, this is part of our research, which shows a chaotic system. And it gives an introduction of chaos by using simple mathematical models. So that's one of the modules, and I like to mention also another one, which is MST 3 to 6, is on fluid mechanics. Although this doesn't cover chaos, fluid mechanics is an area where chaotic phenomena is observed quite a lot. So this could be a good foundation if you want to study chaotic systems, and then study this first and then go to other modules and things.
Brilliant, excellent. We'll come back and talk more, but I just want to take a quick trip to Scott and Sarah and see how everyone is back home.
Yeah, we've got quite a few students coming on. Sarah Green has said that she's starting to see maths in everything since she started her STEM studies. And Catherine Brown has said she wants to make a double pendulum.
Yeah, I'm planning to make one of them as well. But
Any
they are
recommendations on what to make it out of?
difficult. Well, I'm working on it now. It's not easy actually.
So you mentioned both that it's about doing your research and then persuading funders to sort of give you the go-ahead to keep doing some of this research. So a common problem. You're doing something quite interesting, and you talked about the Facebook algorithms and various ways, big data. It's all very topical right now.
Yeah.
Can you tell us a little bit more about the 6 degrees of separation idea and a bit more about how this is applied in a way that maybe people don't suspect? So we're saying maths is all around us.
Yeah, so I mean, okay, so 6 degrees of separation for anyone who doesn't know, I mean, yeah, watch the video on Facebook. But, the idea that I am connected to anybody else in the world by following a path of, I'm friends with Mark, and Mark knows some people and knows some other people, and they know some other people. And you only need to do 6 hops before you can get to anybody in the world. That's the idea. So there's this huge sort of explosion of contacts if you go too far out. So that's the sort of 6 degrees of separation type thing. And of course, certainly the applications in Facebook, I mean, I guess I mentioned Cambridge Analytica earlier. This is exactly the sort of thing they were doing, was they were using the friends of people who had, agreed to share their data with whatever company it was.
Allegedly.
Allegedly, and allegedly we should say. So the idea was then that they were being able to get somehow access to that person's friends. Now, obviously, if they could access their friends' and so on, then 6 degrees of separation, suddenly they can access everybody's data in the whole world. So this gives you some kind of idea why this is actually quite a big deal, why you can get this sort of explosion in numbers of people available and so on. But the algorithms which they were doing, which are perfectly fine, are this sort of market segmentation type things where you want to know whether people have similar interests and so on. So you do little bits of analysis, and some of it will be statistics, of course. There's a lot of statistical analysis in all this, just to make sure that to find out people who might be in. Okay, so a good example. Some years ago now, and this was early days of Facebook, I got engaged, and having announced I was engaged, suddenly all the adverts were about sort of, book your wedding reception here, there, and everywhere. And it's kind of spooky, and you might notice that if you go shopping somewhere, like, you go online and you search for something, then suddenly all of the adverts you see are for those items that you were looking at. So there's this slightly spooky collection, sort of network of things that you can't see, which are talking to each other, working out what it is that you're interested in buying at that time.
But it's interesting because the use of big data, I mean, it's such a topical thing, and you can see how, it's very easy for various companies to click into what you've been looking at on social media or Google, etc., and to then have those things coming up into your feed. But going back to the idea of predicting behaviour, it raises bigger questions, ethical questions, really, about the extent to which we can predict and model human behaviour based on certain attributes. I mean, it's a huge area.
That's sure. I mean, and that's exactly right. And ethics is something that us pure mathematicians particularly, and probably applied ones as well, aren't actually all that good at thinking about, because whenever we have these questions of is an ethics review required, we tick the no box because there's nothing we ever do. But actually suddenly things are beginning to look like there are ethics involved, at least if you're on the applied side of stuff. So you do need to be very careful about this. Yeah.
So, I mean, computers have clearly revolutionised so much of what you're both doing. Where is the future then in terms of what you're hoping to be able to do next? Is it connecting with various other, places, or getting bigger and bigger? And where is it going?
I don't know. For me, we use computers as a tool, personally. Obviously, it's important in terms of applications of what I do, but we certainly use them as a tool to try and perhaps inform our intuition, correct our intuition when it's wrong, because, of course, we make mistakes and so on. I haven't done many of these computer proofs like the 4-colour theorem. That's not something I've done much of. But we certainly simulate things, generate things, to try and get some kind of impression of the area that we're working in and we're trying to get a picture of. And really, for me, that's key to have that image in my mind before I can write down a proof.
Yeah.
Yeah, in applied mathematics, like what I was saying, we have these differential equations, which in most of cases you cannot solve exactly. So then computers, when you need to use it to see how is the solution looking like, and then try to make some predictions based on theory, and then you can check whether it is correct or not with your computers. But yeah, computer is like essential tool in research, in mathematics.
No, absolutely, and makes life so much easier. It's amazing because it's almost like you're using the current things that are there to really help things, and whereas other disciplines might be trying to push forward and say, what could we do if we could do something? It seems like this is a real case of almost like using the tools to sort of support what you're already doing and driving the theoretical ideas and using then the equipment to support that.
Yeah, I mean, that's probably the way that certainly I see it in maths. But of course, the applications will drive the next iterations of quicker algorithms and so on. So, you know, we probably have to write our own computer code, certainly because we're dealing with funny structures and so on. You write your own computer code, and then you learn something. And I have a PhD student who does this at the moment. And, you know, we had some basic piece of computer code which could get up to length 10 or 12, you know, after a couple of days. And then with a few improvements and a few little theorems and bits of intuition, you know, in one particular case we could get up to length 1,000,000, you know, so that's, you know, 4 times, well, you know, power 10 to the 4 times as far as we could get before. Which, you know, what you're able to prove, sort of, there's a feedback loop, I suppose, is what I'm saying. But yeah, I mean that's for us in pure maths because we sort of have to write our own software as we go. I guess maybe you're a bit more.
It's the same. We always try to improve. And for example, we have a model and we try to simplify it. You might look at 3-dimensional systems, then you simplify it to 2-dimensionals. Of course, if you have a much powerful computer, then you could be able to simulate the whole thing. But it's always pushing towards the next step. Yeah.
Brilliant. Well, thank you very much, Mark and Robert, for giving us such an interesting discussion. In the chat, people are talking about whose friends are friends with Donald Trump. So I think we're going to leave them to that.
You all are.
Yeah, don't say that. But thank you very much for an excellent session. I hope you've enjoyed that. We're going to have a short video break where we're going to introduce you to life, health and chemical sciences, and then join us for that next session with life, health and chemical sciences after the break. We'll see you in 5 minutes.